second and third law of thermodynamics. First, to get a vocab word out of the way, heat reservoir. Heat reservoir is just a large source of energy, can be hot or can be cold, that a little bit of, if you add heat or subtract heat, will not make a difference. Like if you had a giant pot of chili and I had like a medicine dropper of ice cold water, it's not going to make a big difference. Just like if I had a bathtub full of ice cold water, one drop of boiling water is not going to make a difference. So when you come across that, that is all a heat reservoir is. It is a heat source that is so large that a small amount of energy change is not going to make the difference. Well, the second law of thermodynamics is there are actually three variations. The first one, and the one we talk the most about, is energy typically goes from a higher concentration to a lower concentration. Now, way back when, Hero of Alexander, I'll come back to that. Hero of Alexander, I believe he is also the one that made great math strides, did Heron's formula, area of a triangle. I'm not sure on that, but I think so. Well, he came up with a steam engine. I'll draw you mine first, and then I'll show you the one, a picture of one in the book. He came up with, it was a pot, and it was sealed except for this sphere, or this ball on top, that had these little pipes coming out like so. Now, this was attached, or as far as there was a stand, and then inside the stand, or under the stand, yeah, no, that's my fire. Just go with it. And so what would happen is they would fill it full of water, the fire would burn, and the water would get hot, it would start boiling, and steam would come up. Well, we know steam rises, hot air rises. So as the steam went up into the ball, it would escape out of the pipes, and it would actually, so that way you can see that it would spin around. Now that you've suffered through my drawing, let me show you the one that's in your book. You can see theirs is obviously much better. It was called, I guess maybe Aleopile. I know that is a terrible, as far as pronunciation of it. But that is as far as the best I can do. So he came up with the first steam engine. It wasn't very practical, but hey, back in those days, he did good. Well, then the one that actually came up with the first practical, we're not going to dwell a whole lot on the history, but just to give you a little bit, Thomas Savery, he came up with the first practical one, and he actually had it to where the water would pump. Well, then Thomas Newcomen came along, and his was the water pump, but it also raised loads. Now, just an interesting fun fact about him, he was a Baptist lay preacher, and he also had pistons and cylinders in his, so that was something amazing. But the trouble was that the pistons and cylinders, they were out of cast iron, so they couldn't get a good seal on it. Also, the cylinder cooled by condensation a step before it needed to, and so the steam would come in the engine too quick before work was done, and it just, let's just say it just wasn't a good situation. Then, of course, a name you are probably familiar from history, James Watt. He actually had machine board cylinders, so there was a good seal. It was also smooth walls. And so his steam engine was the first one we know of as far as it. That's why it was famous during the Industrial Revolution. Now, a sad thing is, 100 years after that, the efficiency of a steam engine was still less than 3 to 5%. In other words, 95% is wasted into the atmosphere. You know how when on a cold day you feel, or even a hot day, you feel your car engine and it's really hot? That's just a good example of wasted energy. Or if you're standing behind a vehicle and you feel the exhaust coming out on your leg, that's heat that's escaping that could be used to run the motor, so it's wasted. So a car engine, it's effective for our person, what we need it to do, but as far as percentage-wise, it could be better. Now, thankfully, our vehicle's a gasoline engine is much better than steam. Also, another fun fact, diesels, they are heavier engine, but they are more efficient. They can be hard to start, difficult to start, so that's why a lot of times when you have a diesel engine, people leave them cranked, but they're a lot more efficient. Well, and then as time goes on, I have another picture for you. An interesting fella came along. His name was Carnot. Nicholas Leonard Soddy, I guess, Carnot. Now, he was a French fella, and his engine was the best yet. Fun fact about him, his dad was Napoleon's Minister of War. A sad fact, though, he died at 36 at a cholera epidemic. There's no telling what he would have accomplished because he had already rejected the caloric theory. And he also anticipated the first law of thermodynamics from this point. So life taken quick, but he still gave us a lot of good things. Now, his heat engine was reversible, and he noticed that with having two different reservoirs, you had a hot reservoir and a cold reservoir. He noticed to make it more efficient that if you increase the temperature difference between the hot and the cold, it made it better. So in other words, if you made the hotter hot and the colder cold, if the larger the difference, the better it worked. And so that is how, and he compared it to a waterfall, or you can compare it to a waterfall. The higher the waterfall is, we'll do a cliff, and the higher distance, the more energy that's going to come out. So he was working on the same principle. The only math in this chapter has to do with his efficiency, and it's the temperature of the hot reservoir, which all this is in Kelvin, minus temperature of the cold reservoir over temperature of the hot reservoir. So if I had, let's say the hot was 100 Kelvin, and we'll say the cold was 10 Kelvin, that's just 100 minus 10 over 100, or 90 over 100. So that would have a 90% efficiency, which is awesome. Now, notice how the closer they are, let's say if it was 100, and let's say the cold was at 80, we'll make them really close. Well, in this sense, 100 minus 80 over 100, so 20 over 100, 20%. So you can see how the larger the gap, the more efficient. Now that makes you think, could it ever be 100% efficient? In other words, could you ever get to a point to make the cold reservoir where it wasn't in play and it was 1 or 100% efficient? And that's what leads us to the third law of thermodynamics. Absolute zero can never be reached. So a process will never be truly 100% efficient. It can be close when you approach absolute zero, but it can never truly be 100%. Now, quickly, because I know this one's going on, let me go back up here and do the other two forms of the second law of thermodynamics. And the next one is you can never be, that leaves where we were now, you can never have 100% efficiency. And then the last one is everything is always in a state of entropy. And entropy is one of those words that to me is kind of fun. It is just the amount of chaos in the universe. And if you want to know how entropy works, go clean your room. Get it all nice and pretty. And then just let it be and just do normal life for a couple of days. Is it still clean? No. What happens is it eventually gets to a point that is right back where it started. So the trouble is that since an object can't stay as far as in perfect sense without work, you can never all of a sudden, unless you're off of Bewitched, you can never wiggle your nose and let everything stay clean. It's always going to go to chaos unless work is done. This is why, as far as on creation, it goes against the second law of thermodynamics to believe in something like the Big Bang, because life doesn't go from chaos to order unless work is done. And so that's another reason why that you know that has to happen. It's everything naturally goes from order to chaos, not chaos to order. Besides cleaning your room, some other examples, cancer is when one cell is abnormal, and then when it naturally goes through and keeps dividing, that's of course how it spreads. The telephone game used to play in elementary school, have someone whisper and then have it go through the room by the end, not what you started with. Even losing your cell signal, as far as in different situations, can be compared to entropy. Heat pumps, just as far as to briefly mention them, heat pumps, they typically, what they do is pump the hot air out. The original heat pumps weren't very efficient, and I remember, I guess it was in the 80s, everyone was going to heat pumps. The trouble was, in the summer, their houses weren't cool or as cool as they wanted, because the heat pumps were pumping all of the hot air out, but it wasn't cooling the air to go back in. Now, since they've changed that, and heat pumps are great and they're very efficient, but when they first came out, not so much. Same thing in the winter. They would pump the cold air out, but it wouldn't heat up the air. Your refrigerator kind of does the same, except it also has a refrigerant in there that cools the air, and so that's why the back of your refrigerator always feels warm, or the exhaust, if your mom ever put shoes at the bottom to dry when they're wet overnight. I know I've done it myself. That's the exhaust from the refrigerator coming out that'll heat it. And very last vocab word, sorry this went long, heat death. Heat death is supposedly when all the usable energy of the earth is going to be depleted and none will be available for work. However, Jesus will come back before it happens. And so this will never truly happen, but that's what it means. Heat death is when all of the usable energy will be depleted. Again, sorry this was a little longer, hard to find a good spot to break it up. Hope you have a great day.